All right, so let me start by thanking the organizers for giving me this invitation to come to Amplitudes and talk about soft collinear effective theory. I think this is the first Amplitudes conference I've been to. Soft collinear effective theory is actually a user of Amplitudes. So I'm going to talk in my talk about how Amplitudes and work from the Amplitudes community from all of you has led to results in this other community. So the outline of my, before I get to the outline of my talk, what can we do with soft collinear effective theory? So what is soft collinear effective theory? It's an effective field theory for collider physics. And so the idea is to describe hard interactions as Wilson coefficients of the effective theory. And then with fields, the collinear region and soft regions of momentum space. And it has lots of different applications, from things about hadron colliders, E plus E minus colliders, the physics of jets, the physics of the substructure of jets, so internal to jets, looking at heavy meson decays, like B decays or quarkonia, even things about nuclear physics. And it helps understand the infrared structure of gauge theory, in particular factorization. So I'll talk quite a bit about factorization in my introduction. Taking resummation to higher orders, it's useful for that. Looking at subleading powers, it provides kind of organizational tools, as all effective field theories do, for organizing the power expansion, and that allows you to go beyond just the leading power description of splitting functions and iconal interactions to subleading power. And then subtractions, I won't say a lot about that, and high energy limit, Reggie phenomena, I'll say a little bit about that. So we're talking about a collision like this one, and I'll show that picture a few times. So here's the outline. We'll talk about an introduction to soft collinear effective theory, some of its main ingredients, and this will just be by way of getting everybody on the same page. I'm not assuming I'm assuming some people have never seen it before. So I'll try to do this kind of in pictures. And then we'll talk about some applications. My title advertises collider physics, so we'll warm up with some E plus E minus collider physics, and we'll talk about some PP collider physics. I may have time to talk briefly about power corrections, and then we'll talk finally about amplitudes in the high energy limit or forward scattering limit, Reggie limit. Okay, so factorization. I want to distinguish two different types of factorization, both which are important for collider physics. The first is perhaps the most important, separating non-perturbative physics from the perturbative physics. So if you think about a collision like this one, proton-proton, the partons and the proton, maybe they're gluons, collide in a high energy collision and produce some number of jets and perhaps some number of leptons. So this is the kind of thing that we study, for example, at the LHC. Then in this factorization here, we're taking a cross-section, we're separating into parton distribution functions, describing the non-perturbative physics of extracting that parton out of the proton, and then perhaps some final state non-perturbative physics, like in this picture showing a hadron here that's a fragmentation product from the jet. So if the jet is a collimated spray of radiation that can be calculated perturbatively with splitting functions, then there's a kind of a final stage where hadronization occurs. And in particular, there would be some kind of fragmentation function to describe this process of extracting that hadron from the jet. And everything else in this picture is perturbative. Perturbative cross-section, you can calculate in perturbation theory. But even if it's perturbative, sometimes there's need for further factorization of the perturbative cross-section, and that kind of brings me to a second level of factorization. And that's because oftentimes what you're actually measuring at a collider may be a little bit complicated, and there may be multiple scales introduced. And so in this picture here, where I'll describe some of the scales. So we have this scale of the hard interaction, where the high energy collision occurred. And then we have scales associated to, for example, the definition of these jets. Maybe it's a jet radius, or maybe you measured a jet mass. And that typically is a much smaller scale than the high energy scale of the collision. And so that's already two scales. There could be some soft radiation in the problem that describes a further scale. Maybe there's a jet veto that tells you that you have exactly 3 jets and not 4 jets. And these things will introduce additional scales in the problem. And when that happens, it's often useful to factorize the perturbative part even further from the non-perturbative part into different ingredients here shown by these various colored functions, beam functions, jet functions, soft functions. And the SCT is doing that by kind of taking advantage of the scale separation in this picture and designing an effective field theory to deal with the multiple scales in the problem. And why is that useful? It's useful just like the part-time distribution functions are universal. It's useful because you get to recycle your perturbative calculations. If you're doing a perturbative calculation and you can use it for multiple different observables, then that's much more powerful than if you have to do a new calculation for each observable. And that's the situation here. In particular, for example, the hard interaction doesn't care about what exactly you're measuring on the jets, doesn't care what choice of jet radius you pick, for example. So it's process independent in that sense. It doesn't depend on sort of what the dynamics of the final state are, but it depends about the exact nature of the hard collision. On the other hand, these functions here do depend on what you're measuring in the final state. The collinear dynamics, the jet radius, things like that will show up in this so-called jet function or these initial state jet functions. And then finally, there's maybe some soft radiation in the problem, and it can also have some universality to it. It could be the same. And I'll just talk a little bit about that in a minute. In this effective field theory, when we separate these scales, the resummation of large logarithms is something that happens through renormalization groups. So we have a standard kind of renormalization group flow between the different scales. We have anomalous dimensions, and that allows us to sum logarithms of the ratios of the scales in the problem. And so if we have a fixed order, we've seen this formula a number of times already in this meeting, expansion, there could be large logarithms. Maybe they're logarithms of lambda QCD over Q. That would be kind of what you get from resumming the anomalous dimension for splitting functions for part-time distributions. But maybe there's other logarithms, could be double logarithms of some transverse momentum that's much smaller than the hard scale in the problem. And typically the kind of resummation we're talking about looks like this, where in some space, you have a resummation to all orders of alpha times log with an extra log that's the double log Pseudokopf logarithm. And that would be called the leading log. And then if you go to higher order, one less log, two less logs, three less logs, then you're getting next leading log, next leading log, or next and next and next leading log. And this is the type of accuracy we're talking about here. Okay, and so using results of high precision calculations to get this kind of precision in the log resummation. So how does SET work? So basically in this process that I drew, we have different fields for the different collinear directions in the problem. So it's soft collinear effective theory, so collinear directions. So in the initial state here, there's two incoming directions, and there'd be a different set of quark and gluon fields for each of those initial directions. In the final state, there's different directions that are determined by the jet axes. In this process, I've drawn three, so there would be three different final state collinear directions, and we'd have a set of fields for each of those. And then in addition, there's some soft fields for describing the soft radiation. And the effective field theory is really telling you not so much about how those fields interact with one another. That's pretty simple. That's really just QCD. But how they interact with one another. How does this one interact with this one? How does this one interact with that one? That's what SET is doing. Okay, so the collinear is expanding about some direction, and soft is expanding with all momentum components small, and the power counting parameter is expanding about either the direction, so collimation, or about small energy for soft. That's what the EFT is designed to do. So it's describing the infrared properties of collider physics. Okay, so let's go step by step. If we think about removing the hard scale in the problem, we collapse whatever was happening in that blob in my figure down to a set of Wilson coefficients. And those Wilson coefficients are multiplied by operators in the standard way. And that's encoding all the hard dynamics of the process. And so that's where immediately amplitude level calculations are coming in to get access to those Wilson coefficients. And we're using that all the time in SET, is to determine the Wilson coefficients for some process. We would use results from the amplitude community. Okay, what about the operators? So in an effective field theory, you should have some rules designed to tell you how to build operators. And it works in a little bit of an interesting way here. So I'll spend a few minutes on this, or a minute or two. So let's imagine in this process that we have sort of two gluons coming in, and maybe one of these jets here is produced by a gluon, and two of them are produced by quarks. We would have some building block fields that we design our operators out of. And there's a pretty minimal basis of building block fields. So there's what's called a quark jet function, which is a quark field attached to a Wilson line, or a gluon jet function, a gluon jet field, which is an analog of this, except you have a field strength attached to an adjoint Wilson line. And these are the fundamental building blocks of SET. And the place that those Wilson lines are coming in is just because it's related to the dynamics of how these different jet directions talk to one another. So let me give you a small example about that. So let's imagine I have a process, this one I've described to you, where I have 2 incoming directions, 3 outgoing directions. And let's imagine that I think about just this N1 direction, one of my jets. Let's say it's a quark. When I think about designing an effective field theory, I'm always integrating out the off-shell regions of momentum space. And so in this process, when I start doing calculations, I should figure out what kind of quark propagators, gluon propagators are off-shell, meaning of off-shellness of order q squared. And if I start attaching collinear gluons that are collinear to this direction to the other lines, then just by kinematics, these propagators are off-shell. So I have to integrate them out. And when I integrate them out, I produce this Wilson line. That's where the Wilson line comes from. The Wilson line doesn't depend on these N1, N2, N3, N4, NA, and B. It's universal for each of these things. And it just combines to the overall color. It kind of matches the opposite, the color of this N1 line. And that's why you get this combination of WN1 dagger, CN1, kind of independent of what you've had attached to it. You know overall that this operator is a color singlet, and that's why you're always getting the same Wilson line, because it just depends on very minimal properties of the scattering. Okay, so that's where these Wilson lines come from, whether it's a gluon in the final state or a quark in the final state. That's why we have these combinations that are building blocks from integrating out the hard regions of momentum space. Now, when we want to make contact to results from the amplitude community, often they're in spinor helicity. And in SCT, we've actually gone and designed, the basis of operators to make our lives as easy as possible. So often, instead of talking about, a quark field like this and building operators with things that have Lorentz indices, we would go over to kind of a set of operators that are in the form that make it the matching to spinor helicity as easy as possible. So we talk about scalar operators with definite helicity. This curly B field that I showed you on the previous slide actually has only 2 components, which are transverse, so I can easily just project onto given helicities plus and minus. And I can do the same thing with quark fields. Then I design currents that have overall fermion number 0 and definite helicity, and I build my operators out of that, and then it makes the matching to amplitudes very easy. Okay. What about the rest of the factorization that I talked about? Well, there's these other scales in the problem. So if I go back to this figure, and I, for example, think about what's happening at this scale, this is the scale which is giving the dynamics of the collinear splittings that are producing the jet, or the initial state splittings that were producing these forward jets. So I get those parts of the factorization theorem from integrating out this scale. And then finally, I have to ask, how does the soft radiation interact with this process? And it actually doesn't know about the internal dynamics of the jet. All it knows is about the color of the overall progenitor for the jet, the parent for the jet, so whether it was a quark jet or a gluon jet, and it knows about the direction. And those things are described by, again, some set of Wilson lines, in this case, some soft Wilson lines. And so often the soft dynamics of a given process, if there is some non-trivial soft dynamics and it doesn't cancel out, can be described by matrix elements of Wilson line operators. Okay. There's also one more ingredient in SCT that's actually going to play a role in my talk when I talk about forward scattering, but it's also important for hard scattering, and that is what's called the Glauber Lagrangian. So this is, instead of having a hard scattering collision, you have a forward scattering collision. And we'll see why that matters later on. So if we think about having 2 very energetic particles that have a glancing collision instead of a hard scattering collision, it turns out that that's a leading order process and can give leading order correct predictions. And so there's in the SCT, once you do the math of integrating out high scale physics, you get 2 different types of operators. One that has a forward scattering between, say, n collinear and n bar collinear objects with perhaps some mid-rapidity soft sector. So that's kind of denoted here. These are some collinear operators, soft operator, another collinear operator, and they're connected by some kind of potential. So this is kind of like what would be an analog of a Coulomb potential, 1 over p squared, except it's 2-dimensional. We have light-like energetic particle scattering, so it's 1 over q perp squared. And we have just 2 different types of operators, one that has between collinear and soft, and then one that has between collinear and collinear. And these operators are describing all the physics of forward scattering, but also they are something that's important in hard scattering for reasons that I'll explain on the next slide. And they encode things like the Lipitoff vertex, which is important for the physics of forward scattering. But the operators here have, higher order gluon interactions as well. So it's beyond the Lipitoff vertex. So what is this Glauber Lagrangian? Why is it important? I was talking about hard scattering. Why did it all of a sudden switch to forward scattering? Well, it turns out that the forward scattering is like the region of momentum space that actually can violate factorization. And it's the only region of momentum space that can, this Glauber region, that can really do so in a dynamical way that is complicated. And so that's why it's important, because actually this Lagrangian is what could spoil the nice factorization theorems that we'd like to use. And it can do so, for example, by having spectator-spectator interactions. So if this is my hard collision, some proton-proton interaction, maybe a virtual photon produced, and there's a secondary collision that's a forward scattering collision, that can violate factorization because it's tying together the two collinear objects in the problem. Often these cancel out, and then you have factorization. They cancel out because of unitarity, basically. Either you're summing over inclusive enough final states, or these exponentiate into a phase that doesn't matter and then cancels out when you're squaring the amplitude. But if there's some phenomena and examples of phenomena that people talk about, which are things like superleading logs or underlying event, these are things that can actually be described by this Lagrangian. In forward scattering, if you want to study forward scattering on its own, then you can actually do that with this Lagrangian. At the end of my talk, I'll come back to studying the forward scattering limit phenomena that exist where this Lagrangian is not canceling out. Okay, so that's it. That's what the theory is. And so it has these three different parts. We have these hard scattering at leading power. We have these hard scattering operators, Wilson coefficients and operators that describe the hard scattering. We have the infrared dynamics and evolution inside this jet function and soft function, high order interactions. They have alpha S expansion. They each have their own Lagrangian. But after this kind of decoupling that I talked about in the factorization, these Lagrangians don't have any interactions from more than one sector. So it's either all n collinear, all soft, all n2 collinear, et cetera. And so this is just a Hilbert space that's a direct product. It's a very, very simple factorized Lagrangian. So the only place that things are talking are through these hard interactions or through this Glauber Lagrangian. So if the Glauber Lagrangian cancels out, then you just have things that factor completely, because the hard interaction is the only place that fields are talking to each other. And that's how SVT leads to these factorization theorems, where the dynamics in these Lagrangians are describing the dynamics of each of these functions, and the hard Lagrangian is tying things together. Okay, so let me talk about some applications. So let's start with something very simple, which is E plus E minus collision. So E plus E minus through virtual photon, virtual Z, producing, for example, two jets, classic process, used in the early days to talk about this discovery of jets and measure alpha S, add LEP, et cetera. So we can talk about a variable called thrust, which basically can be used to pick out two jet events. And in this limit where this parameter tau is very small, our events will look like two jets, two back-to-back jets with perhaps some soft radiation in addition to the collimated jets. And in this case, the factorization is pretty simple. We have some hard dynamics, the hard collision of the E plus E minus. We have some jet dynamics, one of these jet functions, and then some soft dynamics, including some non-perturbative soft dynamics related to final state hadronization effects. And when we use these factorization theorems, we're this term here is allowing us to predict and calculate any terms that go like 1 over tau, or any power of logarithm log to the k tau over tau. And we can sum up those terms with this factorization theorem. But perturbation theory, of course, has terms that don't go like that, for example, are not going like 1 over tau. And so we want to include those terms as well. So we have something called a non-singular cross-section that we add to the factorization theorem. Typically, this is added in fixed order perturbation theory. And it's typically in some small tau region, a smaller effect shown by this blue dashed line compared to the singular effect from these 1 over taus that are resummed in the solid blue curve here. But in some region of phase space, they become comparable, and then it's very important that these things merge smoothly onto one another if you really want to make predictions across the whole phase space of some observable. So this is kind of a classic picture, and it sort of also just leads into the same type of picture for many different observables, where there's some region where resummation is important, some region where fixed order is important. We want to combine them. It can get more complicated than this, but this is sort of a prototypical example. And people have used this, including our group, to do resum calculations and fit for alpha strong. So this is using fixed order results from Gehrman and Weinzel, doing resummation at this N3LL order, including power corrections, which here are described by one single non-perturbative parameter. This non-perturbative parameter at this level of high precision, which we're aiming at kind of 1% level precision, has something called a renormalon, infrared renormalon. That means that perturbation theory has factorial growth. And if you do the calculation in the MS bar scheme, then that factorial growth can be leading to instabilities. And it's an instability in the definition of this parameter that you have to solve. So that's what these subtractions do. Various small effects in order to make high precision predictions for this cross-section. And so in fixed order, this is what the cross-section looks like from thrust up to alpha cube. If you do the resummation, you get kind of much more nicely overlapping uncertainty bands. If you include the power corrections, it kind of shifts things a little bit, but it doesn't really change the picture of the overlap of the bands. And if you include the renormalon subtractions, it just improves the perturbation theory. It converges faster, and the uncertainties get smaller. So this is kind of what these results look like when you get up to the highest order, which is the red band. And we've used that to do fits for alpha strong, and it agrees very well with the LEP data. And we did fits here for two parameters, the non-perturbative parameter and alpha strong, simultaneous fits with the kind of global fit of available data. And one kind of puzzling thing here is that the alpha strong is pretty small. If you know that the world average is 118, the precision of this is such that you should worry about that, and I'll come back to that in a minute. There's various cross-checks that one can do to partly that one wants to wonder about this small value, so you can try other things like thrust moments or different event shapes like a C parameter, and these all tend to agree on this small value of alpha strong. So this is something that's been a puzzle for kind of 15 years. And so, what's going on? There's kind of a 3 sigma discrepancy between this small value of alpha S from these high precision fits and the PDG. And, people have been worrying about this recently, which is partly why I wanted to give this example. So in 2023, there was a reanalysis of everything I told you about, all the by a completely independent group. No common ingredients were carried over, so they just redid the analysis. And they also found a small alpha S. And they did question whether the perturbative uncertainty should perhaps be a little bigger than this, but still find a small alpha S, and so it's not really resolving the puzzle. Another thing that people have been thinking about recently is whether the power corrections could be part of the problem. The power corrections I talked to you about were those coming from a dijet configuration. But when we have jets, there's a question of whether an event is dijet-like. Here, I've drawn the gluon and the quark both going into the same jet, or trijet-like. Depending on the resolution for your jet, you could either be in one configuration or the other, even if you have the same kinematics. If you have a fatter jet, it can hold more. And people have been thinking about whether it's kind of a transition in the description of the power corrections could be responsible for this small value of alpha. I'd say the word is, it's still not clear what the answer to that is, but it's clear that it's something important to think about. And in particular, some groups have done calculations where they've seen in some models that the power correction does change as a function of this thrust parameter. It's kind of like a 30% change here in the fit region. And then other groups, including our group, have done refit analysis of the data and tried to narrow the range of the fit to be more dijet-like, and still found small values of alpha S. So there's ongoing conversation here about what's going on, and it's a very active area of research, and I think we need sort of theoretical progress that goes beyond kind of what's been done so far. Let me talk a little bit about another class of things that you can measure in E plus E minus collider. And we heard a very nice talk by Ian Molt this morning talking about energy-energy correlators. So I'm not going to reintroduce them, but I'll just tell you about some work that has been done on power corrections. And back in 1999, Korchemsky and Sturman had this very nice result that the description of the power corrections for the energy-energy correlator is given by this same universal parameter, omega-1, and now I'm giving you a matrix element definition of it, that describes the power corrections in thrust. So it's an energy operator inserted between some Wilson lines, back-to-back Wilson lines, vacuum matrix element, that's describing that non-perturbative parameter. And the coefficient of this is calculable, so that's very nice. We can make predictions actually for energy-energy correlators based on the results that I gave from fitting this parameter from thrust. And recently, our group converted this MS bar result over to this R scheme result, which basically means shuffling a perturbative series from the power correction between the power correction and the perturbative series here. So this is the MS bar series, for example, and then this is some series that gets modified because you're removing the renormalon here, but you're adding it here to remove the renormalon in that series. Okay, so what do the results look like? So here I'm showing the analytic results of Dixon et al. That's built on the earlier results, which were numeric, and then the next leading order results here from Colorful. And so you see those results here going from leading order to next leading order to next leading order in the MS bar scheme. And if you go over to this R scheme that removes the renormalon, you actually obtain remarkably good convergence. So I'm just showing here MS bar at leading order and next leading order. And in this R scheme, you get results that already start to agree with the data and that seem to be very close to one another at leading order and next leading order. And so this is a result obtained without any fitting. This is a result just taking the values from the fits to thrust, plugging them into the formula, and making a plot. And we were kind of shocked at how well it works, but it's very nice. And it confirms that, indeed, this omega-1 parameter is having that universality that I talked about. Now, you might, if you look closely, see that on the ends there's something going on because the data, which is coming from LAP, Opal experiment, is missing the theory curves. And that's because in these endpoints, you need to do some resummation if you want to make comparison here. In the bulk of the region, you don't. Recently, there's been interest in higher point correlators. You heard a lot about this from Iain's talk. And for example, you can look at an endpoint correlator. And if you have an endpoint correlator, you can define angles between each pair of insertions of the energy operator. So you have energy operator here, you have an angle in between. That's very multidimensional. You can project onto, say, the maximum. That's called the projected endpoint energy correlator, where you just take the maximum angle, only measure that, integrate over the other angles. And that's a nice generalization of the energy-energy correlator to a one-dimensional distribution, but now measuring with n insertions of an energy operator. And we worked out the power corrections for that. It turns out that it's also related to this omega-1, with just some factor that depends on n out front. And we've compared that, done some comparison to Monte Carlo. So this is the 2-point, which you've already seen, but the 3-point, 4-point, 5-point, this formula actually seems to work very well in comparing to Pythia and Herwig. So it looks like this is a good description of power corrections for endpoint energy correlators. In your Iain's talk, you saw this interesting transition that you can make with energy correlators, where you have sort of freely propagating hadrons on the far left in the deep small angle, deep infrared, versus sort of this perturbative region where you're sensitive to the anomalous dimensions. And the anomalous dimension he described as gamma n minus gamma 3, where you get this anomalous scaling in the ratio of energy-energy correlators. And we've checked that, like in this region, the power correction model also seems to be doing a good job of describing the data going from the blue curve to the red curve. So again, without any fitting, this is just taking those values from thrust. There's also some resummation that's needed in this region, so that's included as well. In the other region, in the back-to-back region, so these plots here are very small angle, so this was the part of my figure. The part of my figure that was this part, small angle. Now let's go over here to large angle. You also need resummation on the large angle side. And that has been done up to next to next to next to next. I forget how, the leading log order. N4LL, by Durer, Mistelberger, and Vita, again using a factorization theorem and combining all sorts of perturbative ingredients, including 3-loop hard and jet functions, 4-loop cusp anomalous dimension, 4-loop anomalous dimensions, 5-loop beta function. In their paper, the thing that they were focused on calculating is the 4-loop Colin-Soper kernel, which is a 4-loop anomalous dimension, and gives you something that's very hard to see. There's a little red band here that, where you have nice convergence between the perturbative orders. So power corrections haven't yet been considered. I'm not making a comparison to data here, neither did they. Power corrections haven't been combined with these very high precision results, but that's an obvious thing to work on. Let me turn to PP. So in PP, things get more complicated. You have parton distribution functions. A classic set of variables that's very interesting to study is, for example, the Higgs transverse momentum spectrum. So you have a Higgs boson produced from a top quark loop, recoiling against, for example, a jet. And then you look at small transverse momentum, and you have some distribution where it's got different regions, resummation region, some perturbative fixed order region, some transition in between them. And that's, again, where this technology can be useful. And it's a little more complicated. The factorization has a few more ingredients in it. It has this hard region of momentum space again. It's got some collinear regions that are these ones out here, some soft region. It's got parton distribution functions. But SCT tells you how to put these things together, or Colin-Soper-Sturman as well. So this is a very classic example of factorization. And the result looks like a combination of these various functions that I told you about, which look kind of nice in impact parameter space, where they're just a simple product. I should say that one thing that's different about this plot is that there's a new type of renormalization group that's needed. In the previous examples, I had renormalization group in mu, and that's what we're all used to thinking about from any example of resummation in effective field theory, and having large logs or just running the strong coupling. In this case, the separation of the different objects in the factorization theorem also calls for a separation in rapidity. So this hyperbola here has constant invariant mass, but it has different rapidities. These collinear functions and soft functions live at different rapidities. And so there's a 2-dimensional resummation that's actually needed to resum the logs in this problem. And this rapidity renormalization group is a SCT equivalent to the Colin-Soper evolution kernel, if you're familiar with that. Okay, so the various functions live at various different scales, single scale functions, very nice. You can do the resummation. Let me give you a non-trivial example of that. Like, tons of groups have worked on that. That's a very common thing to work on. Let me give you a non-trivial example, which is putting on top of the theory calculation for this QT spectrum some real experimental cuts. So Atlas has what's called their fiducial cuts, where they put, if you're doing Higgs to gamma gamma, you have a limit on your transverse momentum of your photon, and the second transverse, the other photon, which are 1/4 of the mass of the Higgs or 0.35 the mass of the Higgs. Some limits on rapidities, some rapidity gap in the detector. These are real experimental limits. If you really want to compare theory and experiment, you should put these limits into your theory calculation as well. And that's by putting in some kind of acceptance. But when you do that, sometimes you affect the need to do resummation. So something that might not need resummation, like the total Higgs cross-section, could need resummation once you put these types of cuts. And that's actually the case here, because in this picture here, I'm showing you the transverse momentum of one of the photons. And as you go to the limit of small qt, which is where this peak is happening, you need to do resummation. And by putting a cut of this greater than 0.35, you're sort of forcing the cross-section to be closer to that peak. And it leads to large logarithms, and then you need to do some kind of resummation. And when you do the resummation, you go from this fixed order type analysis over here to kind of a resummed result where things start to converge nicer. And so this group has done that, including all sorts of ingredients coming from the amplitude community. And so I leave it, I won't go through it, but you could look at it. And they've attained very nice results, again, at these high orders where things seem to be converging nicely. They've also done it for Drell-Yan, which is a very analogous process and has super precise data, and again, achieve high precision, including, again, using results from the fixed order community. Okay, so I'm going to skip over power corrections in the interest of time. I only had a couple slides about that. I'm just going to end my talk by talking about Reggie amplitudes. So let me come back to this Glauber Lagrangian. So far in those results that I showed you, this Glauber Lagrangian is canceling out. So let's look at a process where it doesn't, and is interesting to study. In particular, these Reggie amplitudes are something that's often used for the Bootstrap program as an input. So like the higher order structure of amplitudes in the forward scattering limit, large S, small t, is something that's very interesting. What can we say about it from the structure of these, what are called Glauber operators? And so we're again looking at a process where, for example, in 2-to-2 scattering, we'd have something like this. Often this is called an impact factor, and then we have some central radiation region, which I'll call the soft region of momentum space. This Glauber Lagrangian can be used at any loop order. It includes both planar and non-planar diagrams. In this picture, the non-planarity is actually in the blobs, so you can't see it. You can use it with any color channel. There's not really a restriction on the color channel. And the large Reggie logs, which are logs of S over T, get determined by a split in a rapidity scale, which I'm calling nu, between a log of S over nu squared, which is coming from collinear loops, and a log of nu squared over minus t, which coming from soft loops. So that means that if I calculate either the collinear loops or the soft loops, I have two different ways of calculating these logarithms, okay? And that's kind of a nice feature of the effective theory. There's a renormalization group consistency. It's the same as saying I could have Wilson coefficients that I could run down, or I could have operators that I run up, and I have to get the same answer, irrespective of what I did that do. This picture here is just the analog of that in a different space. So how does this effective theory look? These Glauber exchanges, these 1 over p perp squared potentials, are actually just giving you very simple loop integrals that are sort of I pi times a transverse momentum integral. And it's basically the pure cut part of the diagram. If I cut this diagram, it has to be the square of 2 forward scatterings, and that's exactly what the loop integral is, and it's nothing more than that, just exactly that. And this, I should emphasize, these Glauber graphs are not quite the same as what are called regions. So if you're familiar with regions, there's a few differences here. In particular, the colors in this graph includes, for example, the 8 antisymmetric, which in the region graph would not. I'll have a little bit more to say about that in a minute. So how about gluon regiization? So gluon regiization in this set of operators is just the one loop rapidity renormalization of the operators, basically. So if you have this single Glauber exchange, either a collinear diagram, loop diagram, or soft loop diagram, you can calculate the anomalous dimension. And that anomalous dimension is exactly the Reggie trajectory for the gluon. This is the one loop calculation. You can also write down the 2 loop calculation, works the same way. And it turns out that in the effective theory, there's not transitions between a single Glauber and multiple Glaubers. Graphs like this one that can do that turn out to vanish. And that's actually quite nice because it means that this type of one Glauber exchange provides a very natural definition for the gluon Reggie trajectory to all orders in perturbation theory. You don't have to worry about mixing like you do in regions, where you have one region mixing into 3 and stuff like that. At higher loop orders, we understand sort of the way that the renormalization works. So the higher loop order diagram, where you sum over the number of exchanges, number of Glauber exchanges, you have more color channels, you have also more transverse momentum integrals. But in principle, if you define a matrix as that sums over all those spaces, then the renormalization is simply multiplicative, and this correspondence, again, between soft and collinear calculations extends to any loop order, any color. So you always have 2 ways, at least, of doing the calculation. That's kind of nice for consistency and cross-checks. So at two Glaubers, you can calculate the collinear graphs here, the soft graphs there. If you do those calculations, you reproduce standard BFKL type equations for the Pomeron, 8S, and the 27. At 3 Glaubers exchanges, things get a little more complicated. You have a lot of color channels. Of course, you're not all accessible to all those color channels from 2-to-2 scattering, but if you do some more complicated thing, you can access them. You could, again, do calculations from the soft side or the collinear side, and this is sort of, this type of thing is ongoing work that we're doing. So we've done the complete set of calculations here, but we're looking at these calculations at 3 loop order. There's a lot of literature on this Reggie limit, and sort of in the modern language, I think this Wilson line Reggie effective field theory has gone the furthest in terms of perturbative amplitudes. So work by Cron Hewitt as well as Gardy and collaborators. And from our point of view, this is sort of interesting to think about because like to get this SCT, we did a top-down matching from QCD just directly onto SCT. And so we'd like to do matching of this effective field theory onto the Wilson line effective field theory and understand the correspondence between these two languages, which I think is very complementary. So I'm just listing a few things here, which maybe, there's a lot of more work here than in SCT, but I think like some things that this could benefit from making this correspondence would be like in SCT, we have operator definitions for those impact factors, those collinear, those J functions are not something that's obtained by full theory minus the Wilson line EFT, but rather obtained by a direct calculation within the EFT. We can do collinear loop calculations for the rapidity logs. Sometimes those are easier. So that's interesting. And the nature of things that vanish is different. So that's something that would be very interesting to understand from between the two languages. And also the symmetries, the way that the symmetries are realized are different, either from the start, where symmetry and crossing are built in, a signature and crossing are built in from the start in this theory. In this theory, it's more like a quantum field theory where those things come out perturbatively, order by order. Okay, and finally, I should mention that this is sort of all forward scattering, but I come back to this point that this type of technology and these type of diagrams could also then be input into hard scattering to understand factorization violating phenomena. Okay, so this is the end of my time. I haven't talked about a lot of applications, but I've made a list here of some other applications, B physics, jet substructure, electroweak logarithms. There's other applications of SCT, even to dark matter or gravity. And so I'll just close by showing you my summary slide here, some of the examples we've talked about. We skipped over power corrections, but other than that, I gave you examples of non-perturbative corrections, resummation, and these Reggie amplitudes. Thanks.
Okay, thank you very much for this very beautiful talk. So do we have any question for Iain? Oh, yeah.
I have 3 questions.
I'll take all 3 of them.
So first, slide 17. I mean, the Glaber-Lagrangian,
Yeah.
can you take it to model, say, color singlet exchange from Higgs production in vector boson fusion?
Yeah.
Okay, so you could see factorization violation there, for example.
Yeah.
Okay. Then about the Higgs PT distribution.
Yeah.
We actually, the chair and I and some other people
Yeah.
have the most advanced amplitude for Higgs PT distribution because it includes the full top mass and B mass dependence.
Yeah.
Could that be folded together
Yeah,
with this?
I think it could be folded in to the hard functions here, and yeah.
Okay.
And the fixed
Okay.
order inputs.
So, third question. I observed a few years ago, just doing some numerology, a correspondence between the one loop impact factor,
Yeah.
the high orders in epsilon,
Yeah.
and the final part of the two loop trajectory.
Yeah.
Is this something that?
Yes, we've looked at it actually, and I didn't have time to talk about it, but it's quite interesting. And it turns out that the way that the effective theory works is that there's connections between diagrams coming from crossing symmetry, and some of those connections actually are related to the things that you studied. Basically, there's connections between soft loops, which are giving logarithms, and Glauber loops, which are giving I-pies. But those relations are true because there's symmetries, they're true to all orders in epsilon. And because of the structure and simplicity of some of the diagrams, they make predictions like where a one loop diagram has two loop anomalous dimensions in it, for example, at higher orders in epsilon. You do a one loop calculation, for example, of just this diagram, and the finite correction is proportional to exactly the two loop cusp anomalous dimension, and the order epsilon part of this is proportional to exactly the rapidity anomalous dimension. And you can understand those correspondences through this use of symmetry and crossing in this theory. But I didn't have time to get into it, but
Okay.
yeah.
And is there any way to carry that over to the next loop?
I think so. It hasn't been done, but it should be possible, yes.
Okay,
Yeah.
thank you.
Hi, can I ask one question?
Yes, very quick question.
Uh, yeah, so my question is that like if at the amplitude level, if we do the method region, we have to care about the possible overlap between different regions, right?
Yeah.
And but here, is that possible when we do, for example, the rapidity renormalization of the operator?
Yeah.
Is that possible to have mixing between the soft operator and the collinear operator?
Yeah. So when you, and that, again, is something I didn't talk about, but technically when you have these different regions and you calculate these functions, you often have subtractions. And it depends on your exact choice of regulator, what those subtractions look like. But you might have a subtraction on a collinear function to remove the soft region so you don't do double counting. Yeah, and I'm kind of doing that all under the hood without telling you.
Okay.
Yeah.
Thank you.
Okay, then let's thank again Iain.